Coulombs Law is named after this guy named Charles Coulomb, and all it states is the force between any two particles, A and B, depends on only two things, okay? One is this thing called an electrical constant. Let me zoom in, okay? And it's just a big number that you have to measure in the lab. Don't worry about it, but it's 9 times 10 to the 9th is the number we're going to use to plug in. You don't have to worry about how it was derived, okay? And it's got weird units because it's just an electrical constant of proportionality to make the equation work, okay? Don't worry about it. But the big idea is it depends on how much charge you have on each object and then the distance between the charges, but it's distance squared. And then you'll get a force in newtons, which is a technical metric unit for force. We're used to force in pounds, but the technical unit is in newtons. Normally, most people don't have to worry about this, but someone who's designing a memory chip for your digital camera, if you're looking at making a new printer where you want the toner to stick to the paper and you charge up the toner electrically, then you got to be able to calculate this, okay? So we're going to look at understanding this conceptually, and then we're going to do some simple examples down here, okay? But it's almost kind of common sense, and really the kind of math I want you guys to get out of this, I'm going to do a little simple demonstration up here, okay? Is conceptually we want you to understand Coulombs law. So how about this? Here I got a can, a pop can. True or false, there are electrical charges in this pop can? The answer is it's true. There are. Okay? It's just you don't get shocked because, again, they're electrically neutralized there, right? However, I can prove to you that there's electrical charge there by attracting charge in there by charging up an object, okay? So let's say I put some electrons on here. If I want to get more electrical force of attraction, I should put what? More or less charge on here? More. So let's say I put on twice as much charge. So according to Coulombs law, there'll be now twice as much electrical force. But the other factor is what? Is the distance, right? So Coulombs law simply states that it's the amount of electrical force depends on the amount of charge present, and then it's 1 over the distance squared. That's the key. So if I move twice as close, there's not twice the force, but what? 4 times the force, right? If I go 10 times closer, there's what? 100 times the force. You see that? So again, what's really going on is Mr. Lau sold his soul to the devil. 666, okay? So it looks like it's a magic wand, but it's not. It's simple electrostatic attraction, okay? And I can apply Coulombs law to increase or decrease the amount of force present there, okay? So how about practical stuff? Let's say you're out in the middle of a golf course and a big thundercloud rolls in. If you are twice as tall as the nearest person next to you, how much more likely are you to be struck by the thundercloud? Aha! Not twice as much, you're 4 times more likely. If you stand next to a tree, and the tree is 10 times taller than anything else on the golf course, you are 100 times more likely to be struck. See that? So understanding the basics of electrostatics is important in nature there, okay? So let's do a quick example down here, okay? Here we have 2 charges, Q1, Q2. Q is symbol for charge. Distance is 1. You get a force of 1. We just pick some easy numbers, okay? If you double the amount of charge, you'll get double the force. How about this? What if you double the charge on both A and B? Don't worry about the units, okay? How much more force will you get, like we just talked about? You will get 4 times the force. You see that? What if you double the distance, but you keep the charge the same? If you're twice as far, okay, why is it 1 over the distance squared? If you move something twice as far from something else, they both end up moving twice as far from each other. So what's 1 over 2 squared? It's 1/4, okay? You'll get 1/4 the force there, okay? So if you move charges apart, the force becomes exponentially weaker, okay? Finally, what if you double the charge and you double the distance? What would be the net effect? Well, doubling the charge on each object would give you 4 times the force, okay? Doubling the distance would be 1 over 2 squared, or 1/4 the force, okay? So 1/4 times 4 is no change, okay? So the point of that is, why would you ever want to figure out something like that? Well, most of us don't care, right? But let's say you want to build a cool electronic reader, so all your books in the future can fit on a little device right in your pocket there, right? And if you charge up an electric ink particle and you want it to stick on a screen, you need to know how heavy that ink is, there you go, and how much charge you should put on there so it sticks to the screen. You see that? Cool, right? Ah, don't touch my computer. There you go. Fun, okay? If you put on too much charge, that's bad, because this thing actually then gets stuck to the ceiling and it's really hard to get down. There we go. Fun. Ah! There we go. Okay? So anyway, in a nutshell today, we wanted to introduce the basics of electricity and electrostatics, and to apply the big idea that charge is always conserved, and we can actually quantify that charge in terms of its force via Coulombs law.